Great. I'm absolutely delighted to welcome all of you to the defense of Tony Hugh. Thank you all for coming. My name is Hugh. Herr. I'm Tony's primary research advisor. Tony got his undergraduate at Georgia Tech in material science, and then came here to the MIT Media Lab for his master's. And today he's going to tell us about his PhD work, bone-anchored mechanoneural knee prosthesis to enhance control and embodiment. The general outline is that Tony will present for approximately 45 minutes. Then we'll open it up to a general Q&A to the public. I'll then ask everyone to leave except for Tony and the committee for further questions and discussion. So without further ado, Tony, please take it away.
All right, well, thank you everyone for coming today. Very excited to be here, finally. First, I'd like to thank my committee, who are outlined here. So Professor Hugh, Herr, Professor Rickard Brånemark, who's on Zoom, and then Professor Nidhi Seethapathi, who's also here in person. So I'll begin with a little bit of history. 30 years ago, the most advanced prosthesis you could buy on the market looked something like this. It's a mechanical device. There are no motors, and it has rudimentary gait capabilities. And that's as far as we got over thousands and thousands of years, prehistory, millennia of amputation. In 2023, Utah released this video showing a powered knee prosthesis, a powered knee ankle device, with rudimentary EMG control. And what I mean by that is there's a sensor that is on the subject's residual biceps femoris, and they can use that sensor to do a few things, to do squats, to do lunges. But here's a limitation of the paradigm. We have all these amazing sensors on board. We have IMUs, we have torque sensors, load cells, we have encoders for the joint angle, and we have a single EMG. But actually, the most amazing machine in this picture has nothing to do with the prosthesis. You actually can't see it. The most amazing machine is the human nervous system, the central and peripheral nervous system, and also the human neuromuscular system. Why, in all these thousands of years, are we not taking advantage of these mechanoreceptors, these sensors, these biological amplifiers? Why are we not modifying the hard tissues and the soft tissues to better integrate humans and devices together? The traditional engineering approach is to simply try to build better mechatronics in the hope that you get a better rehabilitation outcome. But I don't think that's quite right. So I'm proposing another paradigm. I'm going to take the traditional, conventional transfemoral amputation. I'm going to modify the soft tissues. And in addition, I'm going to add a titanium implant, modify the hard tissues, and embed and implant sensors so that we can extract the control signals we need to further rehabilitation. So I'm standing in front of you today. That means I've actually done it. And if you're paying attention, these next 2 minutes, I hope, will be very interesting as I show you our results. Oh, and we have the robot.
Gentlemen, we can rebuild him. We have the technology. We have the capability to make the world's first bionic man. Better than he was before. Better, stronger, faster. Oh, yeah!
Definitely going left more than right. Soccer.
Truth is, I am Iron Man.
Okay. So, thank you. That's what we accomplished. I'll tell you how we did it now. But let's first start with the motivation. There are hundreds of thousands of transfemoral amputees in the United States, and there's an incidence rate of over 100,000 every year. So it's a growing issue that we need to address. When you have a transfemoral amputation, you develop gait asymmetries, which can lead to osteoarthritis and other secondary comorbidities. This is due to the lack of functional joints, which affect your posture, your gait, basically everything about your movement. And additionally, just to rub salt in the wound, as you get older with a transfemoral amputation, you become less and less mobile as your other health issues related to age start compounding. There are some solutions that we have today. I showed you earlier the passive mechanical device, which provides basic support in walking, but it doesn't have any actuation, it doesn't have any control, and it's essentially a fancy stick. We also have variable damping prostheses. These allow you to adjust your damping as you go through gaits with some terrain adaptation. However, there's actually no motor in there, which means that you can think of it as more of a shock absorber. It's helpful, but it's not all there. And then finally, there are 3 powered devices on the market today. There's this knee, which can assist you getting out of a chair. There are other devices which can help you with stairs, as they're showing here. And this one can actually help you transition to a cycling gait and allow you to use a bicycle. So these provide positive power because they have motors. But because they rely on sensors on board the prosthesis, they may not be accurate in terms of predicting your next movement. So you can think of it as an electric scooter, but it's not your body, right? It's not a limb. All of these paradigms, they follow this pattern where the human and the prosthesis exchange energy, but not information. You're in the back seat at all times. You're not driving. And what we really need to do is marry the human and the prosthesis together and exchange energy plus information from the nervous system in both directions, both efferently from the central nervous system and afferently back to the central nervous system from the device. And if we do that, we can do amazing things. So my thesis objectives are 3. First, we're going to augment the soft tissues. We're going to take our flesh and we're going to improve upon it. After that, we're going to integrate implants. We're going to add technology, artificial components, and we're going to marry them to the hard tissues, so nothing goes to waste. And finally, we're going to develop a controller that can take advantage of all of these components that we've created and actually do something amazing with them. So my first aim specifically, augment musculature, but see if it can restore proprioception and muscle control. My second aim, integrate implants through this technique called osseointegration so that we can directly load the skeleton, which is the part of our body that's supposed to be loaded, and ideally allow us to extract signals from the muscles themselves in a more clean and high-fidelity way. And finally, when we enable direct control, we're going to enable a continuous modulation of joint torque impedance. So that way, you're always in control, and you always get what you want. Okay, so we're going to start with aim 1. For a little bit of background, our muscles work in at least pairs, as in there's an agonist that contracts, and then there's an antagonist which stretches. And by having muscles come in at least pairs, we can go both directions with our joints. The generic term, as I mentioned before, is an agonist for the contractor, and then an antagonist for the muscle that experiences stretch. And then when muscles deform, when they stretch and when they contract, they actually send signals back to our central nervous system. So we get afferent muscle spindle feedback, length and velocity terms. And we also get Golgi tendon feedback or some notion of force from our mechanoreceptors. And you can see here how it all integrates in the central nervous system with our spinal cord, our brain, our muscles, our mechanoreceptors all together. So in the conventional transfemoral amputation, we have muscles that are there and soft tissues, but they're mainly intended for padding with a prosthetic socket. The surgeons in the current age mostly do not care about these fanciful control patterns that we work with in the lab. So if that's the case, then your agonist and antagonist pairs are actually not such, and you have muscles which are basically pulling against an infinite impedance. It's as if you're pulling against a brick wall, and many subjects report that they feel as if their ankles or their knees are locked in place, as if they were a ski boot or if they were like a brace. So this is pathological, and we need to fix this. In our lab, we've actually developed something called the agonist-antagonist mechanoneural interface that you can see on the left. This is a mechanical configuration where we have muscles which are naturally paired, repaired in a surgery, so that when one contracts, it stretches the other and provides a sense of phantom joint proprioception, or the sense of the body in space. You can see how the structure is very similar to our physiological configuration on the right. So what I want to know is, can we actually bestow this agonist-antagonist relationship to someone with an existing amputation? Previously, we've done it with persons who have an acute surgery, as in it's their first time with an amputation. We provide this configuration, we see how they do. But what if we can take someone who already has an amputation with all of the loss of musculature and physiology and provide this benefit? And so the goal is, even if we provide this mechanical configuration, does it work as we know the acute case to work? Which brings me to my experimental design. Here, we have a conventional amputation, or someone with a conventional amputation. We provide the revision as an acute intervention, or as an intervention. We wait for this person to recover, and then we perform an assessment on the recovered soft tissues. And we do the same testing both pre-op and post-op so that we can actually understand if there's a within-subject difference. So we did this with 2 subjects, and here's how they did. So specifically, I wanted to test a few hypotheses first. Does the transfemoral AMI revision restore greater neuromechanical function? Do the muscles work better with the nerves? Does it restore greater neurophysiological function, as in does the central nervous system adapt and become more physiological? And finally, does this actually benefit in terms of control of movement, control of phantom joint position, and ideally generating signals that we can use to control a prosthesis? So our 2 subjects are here. They're rather different. One has been an amputee for 4 years. The other one has been an amputee for 22 years. So with longer amputation times, there's more atrophy. Additionally, one has also suffered trauma, which means that they did not decide how much tissue was lost. We kind of get what we get. So let's see how this intervention affects these 2 subjects. The first test we did is measure the muscle contractions and deflections while we collect ultrasound. Ultrasound tells us the exact state of the muscles within the body. And the result is that we can actually determine how much afferent information, how much feedback from the constructs or the muscles is going back to the central nervous system. So remember that we performed the same test before and after. We performed this ultrasound test before the intervention and after the intervention. You can see here by the results in the middle, the net antagonist neuromechanics, as in the amount of information from the muscle that's being stretched minus the amount of information that's being generated by the muscle that's contracting. We see that in the post-operative condition, in the colored traces, that we get more information back to the user. And this is completely dominated by afferent stretch response. So because we bestowed the mechanical interface and the configuration, we increase the amount of afferent feedback through that, and we can actually measure it with this paradigm. So that's great. Neuromechanics are restored to at least some extent. We can also do a neurophysiological test where we take the subjects, we put them into an MRI scanner, and we ask them to perform phantom knee movements while they're in the scanner. When they do this, we can detect the blood flow within their brain, and then we can determine if there's more activity that's corresponding to movement of the phantom joints. And so if you look on the right here, we have pre-op on the top row, then post-op on the bottom row. Preoperatively, there's little activation in the supplementary motor area and motor cortices. However, after the intervention, when we do the same test again, we see significantly increased activations in the proper areas of the brain. So not only did we restore neuromechanics, but we restored neurophysiology with this intervention, which is actually quite an amazing result, that we can make a change in the peripheral area and then get a result back in the central. And finally, we want to test if the subjects that we have actually perform better in terms of control. So what we have here is a person with an intact ankle subtalar who is moving their joint. And then we see the corresponding activations from the muscles on the left, right? Okay, so it's easy when you have an intact joint to measure how well someone performs, because there's a map from muscle activation to the dynamics of the joint. That map is this F function here. However, when someone has an amputation, you can't play this trick. You actually have to pull back your observations into this domain of abstract noumena, this domain of intended dynamics. So we can still record EMG from persons with amputation, but we have to interpret it in a very intentional way. To do this, I borrowed a tool from another lab member. This algorithm, it takes EMG that we observe through electrodes. It decomposes the EMG into geometric boundaries, which represent intended movement directions. And then we can interpret the EMG as an intended movement direction with a corresponding level of effort. So that's great. We can now figure out if someone can actually move or make EMG patterns that correspond to better movements. Okay, so we took this algorithm, we measured signals, and we created a graphical user interface which gave visual feedback to the subjects so they could see how much they're activating a certain direction of movement. Here are some example traces. So you can see that on the top half and bottom half, we have our P1 and P2, our two subjects. For each top and bottom half, the top half of that is the preoperative condition, and then the bottom half of that half is the postoperative condition. Essentially, blue is good. Blue is the intended movement direction. Orange is the coactivation of the movement direction that we don't want. So in the preoperative conditions, we get a lot of coactivation in terms of movement intent. We get mixed signals. In the post-operative condition, on the bottom of each top and bottom half, we see a lot more blue, a lot less orange, and also the activations are graded. So at 25% effort, 50% effort, and 75% effort, they go up. This is correct. This is what we want to see. So great. Not only does our peripheral intervention restore neuromechanics and neurophysiology, but it also helps us improve our motor control. And then here are some statistics related to that previous test, which show that to be the case significantly. So in the post-op, you see that the target channel activation is graded with effort, as in the orange line goes up with the x-axis. However, in the pre-op condition, it goes down, as in the activations are more sparse and erratic, and overall not what we want. So to conclude, for AIM-1, in a pilot study of 2 individuals with revision AMI, we find that neuromechanics and neurophysiological function are recovered and improved. We also find that there's a causal relationship between improved neuromechanics and improved efferent control. That's great, and we have a publication to show how great it is. Great. So let's move on to AIM-2, where we integrate implants and see if we can add on to this soft tissue intervention to improve it even further. So the goal here is to take the revisional AMI, incorporate the implant, which allows us to directly load the skeleton, the thing that's supposed to be loaded, and also extract the signals directly from those transfemoral AMI constructs back through the implant so that we can use them for control. Let's see if this works. A little bit of background first. So osseointegration, which is the act of essentially fusing titanium to bone, it was really developed by a man named Per Brånemark, who developed it for dental implants. He had at least one son, Rickard Brånemark. And Rickard Brånemark took that idea and really ran with it. He pushed this notion of, well, if we can put teeth into people using this technique, why can't we do it with prostheses? So sockets, prosthetic sockets are very uncomfortable. They have a lot of issues related to their use, such as skin irritation and poor mechanical transfer of energy. But if you can directly load into the bone with this idea, then you can absolve a lot of those issues and get past that. And it's been successful at all levels of upper and lower extremity amputation. You can see how it just passes through the skin permanently. That's an interesting part, but we won't talk about that. So with osseointegration and the system that's developed by the Brånemarks is called OPRA, we eliminate socket issues. We facilitate proprioception and osteoperception, so sensation through the bone itself. We allow ourselves to use prostheses in a more graceful and appropriate way. And we also improve range of motion and limb strength because you're not wrestling with this hard socket interface with soft tissue dynamics. So it's better. So going back to AIM-2 for this study, let's take the transfemoral AMI revision. Let's add on the e-OPRA system, which in addition to all the mechanical benefits that I've discussed earlier, has all these electrodes that we can use to read the constructs running through the center of the abutment. And let's combine this as the OMP platform. The OMP stands for Osseointegrated Mechanoneural Prosthesis. So we're stacking soft tissue technologies, hard tissue technologies, and we're hoping that each component works individually and together. So we actually had 2 subjects go through this pilot study to receive the OMP in a revisional case. My hypotheses are that the OMP system successfully osseointegrates in the presence of all these soft tissue constructs and electrodes. And I also hypothesize that we get better signals out from the prosthesis, the abutment, because we can put the electrodes closer to the muscles, and we can always keep the electrodes in the same place, as opposed to a surface electrode, which you take off, reattach, you sweat through them, etc. Okay, so the timeline is actually rather involved. There are 2 stages to the surgery. In the first stage, you create the AMI constructs. You place the screw that goes inside the femur, and then you allow that to heal for up to 6 months. So in the bottom left, you can see that we have x-rays of this post stage 1 condition. In stage 2, we go back and do another surgery. We take the muscles, we implant the electrodes that we are going to route through the abutment, and we actually attach the abutment itself, which is the part that sticks out of the body, okay? And then there's an entire rehabilitation process which comes afterward. So post-stage 2, you can see that both of our OMP subjects, they have the entire implant, they have the electrodes, and they receive the cortical window, or a little hole through the femur, that allows the electrodes to pass from the muscles through the femur into the middle of the abutment and come out the bottom, so that we can actually use them for control. So great, this works, I think. Well, let's see. Here, we have a figure that shows reduced lucency after bone remodeling. What I mean by this is if you look closely on the left, you can see that there's a lot of lightness around the screw threads. That's because that implant just got placed and the bone hasn't had a chance to remodel. However, if you look at the right figure, you can see that a lot of that lightness is filled in with darkness, so higher density material, hard tissues. And that indicates to us that the implant has successfully osseointegrated. And there's a really easy way to tell if this works. So I don't see any legs falling off. Let's move on. That part works. Okay. So in addition to the hard tissues and the implants, we actually have to test the electrical components. We have the intramuscular electrodes. And then I tested the impedance of the electrodes. You pass a 1 kilohertz carrier wave, AC, into the electrodes and see what the basic impedance is, the linear portion. We see that from basically 0 to 200 weeks post-op, especially with our first subject, who we tested at 192 weeks post-op. We see that the impedance doesn't change. We expect about 1.2 kiloohms for each electrode. That's what we see here. We don't expect there to be some nonlinearity in the middle where electrode impedance goes up and down and up and down. We kind of expect that if it's a certain value at the end, it's basically been that value the whole time. So that's great. The electrodes are stable and the electrical characteristics are known. We can also perform a test to determine the signal-to-noise ratio that we get from the muscles. So we do that with this equation here. We just ask the subjects to make a maximum volitional contraction of the muscles that we're interested in and just see how much signal we have above the noise floor. So for both subjects and both muscles that we're interested in, which are the rectus femoris for knee extension and biceps femoris for knee flexion, we see that we have about 30 decibels of gain. So 30 is what we expect from intramuscular electrodes based on literature. Things are working. Perfect. Let's continue. One really big advantage of implanted electrodes is that we can get closer to the source of the signal. So EMG follows inverse square law. If you have surface electrodes which are really far from the muscle, you get a poor signal. And we can actually test this by having subjects perform the same movement and measure simultaneously through the intramuscular electrodes and from surface electrodes. You can see here I've defined a signal power ratio as the power of the intramuscular electrodes signal over the surface signals. And we have 1.3 for OMP2 and 4.2 for OMP1. So this is a gain in information. More information, better control. Why did we have a gain in information? Well, if you look at the ultrasound here, we can look at the muscle depth from the surface of the skin. OMP1's muscle, this is the rectus femoris, by the way, is 3.3 centimeters below the skin surface. OMP2 is 1.1 centimeters below. So we don't have hard numbers, but it seems that, yes, indeed, physics holds and electrical signals follow the inverse square law. Okay, so to summarize, in a pilot study of 2 individuals, we confirmed successful osseointegration. The people can walk without issues. We confirmed stability of the electrodes, and we confirmed their integrity of signal. That's great. There's a publication that we put together for this. Okay, so here's the interesting part. Here's the part that kind of ties it all together. We actually have to make the things that we did, the soft tissue constructs and the hard tissue modifications, we have to make them useful. This is really hard because we think the body's going to do one thing and then it decides to do something else. We kind of have to follow it a little bit. We kind of have to massage it. So in this aim, I designed a controller to provide continuous modulation of joint impedance, joint forces, joint position, joint stiffness, damping, all of that, so that the person can actually drive the car. The person can be in control, can be unified with the prosthesis and feel as if it's part of their body. Okay? It takes steps. There are steps to this process. The first step, we have to read and digitize muscle signals so we can use them as control input. We have to compute the desired torque impedance values that we want at the joint from those signals, in addition to onboard sensors on the prosthesis to fill in the gaps of information. And finally, we have to make a real leg do all this stuff. We have to make sure that we tame the beast, make sure the mechatronics are appropriately controlled. And that way we can finally get what we want. So let's start with the first part. Typically, when you have surface electrodes, as you see on the left here, here is a subject with transfemoral AMI who does not have the osseointegrated implant. When you have surface electrodes like that, there are impact artifacts which can be conveyed through the sensors via just loading of the socket, unloading of the socket, changing impedances through sweat, all of those complications. So we have to develop an algorithm, and another lab member helped with this. We have to develop an algorithm to filter those impact artifacts out and generate usable signal from the values that we do read. That's this middle part here. But once we get that, we can actually estimate a level of muscle activation, which is normalized between 0 to 1. 0 being there's no activation, 1 being that there's full activation. And we can use this value, hopefully, in clever ways, depending on how clever you are. So that's the pipeline to get EMG into a usable signal that we can use for control. And just in contrast, in the OMP case, we plug in directly, and we actually avoid all of those impact artifacts. Hypothetically, we'll test that. But it's a plug-and-play operation. You don't have to place the electrodes. You don't have to palpate the muscles to figure out where they are. You can just plug in the jack, and you know that the leads go into the right places if nothing's changed. Okay. And then just to summarize all the steps and put them into a little nice block that I showed you earlier, that's here. Okay. This middle section is the mathy part, although I've removed all the math for you. We need to actually calculate what torque we should generate at the joint based on the signals that we do get from the muscles and from the onboard sensors of the prosthesis. So what I have shown here is that we actually do have a finite state machine on the device. There's a control loop that actually tells us if the leg is on the floor or if it's in the air. And we need this for a few reasons. Most importantly, the mechanical knee here, the mechatronic device, it has a lot of inertia. It has a transmission, which means that you have reflected inertia through that transmission. We have to compensate for its dynamics. And to do that, especially for things like level ground walking and gait, to make the knee swing appropriately and freely, we just have to know a little bit about what the device is doing itself. We can't just use muscle information directly. We have to tame the beast. So that's one part of the computational layer. And you can see that with just that part, you get good walking, right? There's no neural information here. The subject here is simply in the backseat of the car again and going forward. But in addition to that, and this is the part that makes it cool, we can use muscle information and calculate a torque that's overlaid over the joint. And we can determine through that torque the joint's set point, its damping, how much energy it absorbs, and its stiffness, or how much it resists motion away from the set point. So muscle activation, 2 signals from the rectus and biceps femoris can vary these parameters and give us the torque that we need to do what the human wants. And I've turned those colorful words into colorful lines, but there's some math involved. And just to go back, so this figure again, what we did in this step is actually we developed an F. We developed a function that maps muscle activation to dynamics. Specifically, this third definition of function F, controllers that map activation to prosthesis impedance in the case of an amputated limb. So when we do this, we can actually make a joint behave as if it's a physiological agonist and antagonist pair operating around a mechanical linkage. Great, fantastic. We now have 2 out of the 3 layers. We need to add the third one, which is the actual physical device in the real world. We need to control a knee based on the desired torque that we calculate from the middle layer. Okay. So here on the left, you see the device that we've developed. This is the hardest slide of my entire thesis. This was very difficult, but we did it. We did it. That's the most important thing. We developed a series elastic knee with the appropriate stiffness of the series elastic component, with the appropriate transmission, with appropriate control, and the computational hardware. We added the right sensors so that we can determine when we're on the ground versus in the air. And we married them all in a mostly reliable fashion using the connections, the wiring, and the code on the right. So with this system, I closed a controller around it so that we can actually get the desired torque out from the device that we demand from it from the middle layer. And you can see that once we tame the beast, once we have the appropriate control architecture, we can get about 10 hertz closed loop bandwidth. It just means that the device can swing around really quickly, fast enough to model and replicate what a real knee does. Okay, and just let's put all the steps together like Lego. We have muscle activation to control calculation to actuation. And when I demonstrate that on my arm, it looks like this. Okay, I've demonstrated that in free space in the air, but it also works on the ground. So for aim 3, let's bring it all together. Let's take 3 cohorts of subjects, those with conventional amputation. Let's pit them against those with AMI, acute AMI, or revision. And let's pit those subjects versus the OMP subjects that we discussed earlier. And they're not actually competing. It's not like a competition. It's science. But we have 3 cohorts in our study. And we're going to compare the physiology, the control ability, and the resultant sense of whether or not the prosthesis is a part of your own body. Okay? So I have a few hypotheses. I think that the OMP is going to win. I think it's going to provide outsized improvements in prosthetic performance, especially given the physical nature and qualities of our 2 OMP subjects. And I think that with improved control, we actually get better sense of prosthetic integration, this abstract notion of the device belonging to yourself. Okay? So just...
Hey, come check this out. Tony's giving his thesis, his PhD defense right now. He's about to show the grand finale.
Thank you.
Which is very impressive.
Spoiler alert. Okay, so here's the grid of the different categorical differences between the subjects. OMP basically has all the improvements, the soft tissue improvements, the hard tissue improvements, and the signaling improvements that we've made. And then the other 2 groups do not have all of them, okay? And then on the right, you see the figure of the loop going from the brain through the prosthesis back into the bone that goes back, so that sends signals back into the brain, okay? Here are some subject metrics. The main thing that I want to point out is that I did not have any advantages in this competition, okay? The OMP subjects, they are older than all the rest of our cohorts. I mentioned in the very beginning that older transfemoral amputees tend to have more difficulty with ambulation. They're also the longest out since their original amputation, right? So that means they have a lot of muscle atrophy and they are disadvantaged in terms of signal production and likely muscle control. And just, not to be mean, but we have a chart, a figure of BMI on the y-axis on the left, and then time since amputation on the bottom. And we expect, if we travel along that y-axis, that we get lower performance ability, lower agility, right? You can see that where our OMP subjects end up relative to the rest of our subjects in the cohorts, okay? So I did not have any advantages, but as you saw in the video earlier, we made it work. And I also like to point out that there are 2 levels, K levels of subjects that we work with. K3 implies that you're able to walk around, but you're not doing extreme sports like running or jumping or hiking. K4 means that you're a very active person with the amputation. You can typically go out and about and do like adaptive surfing or snowboarding, things like that. But we have a mix of those 2 K levels within our population, and we'll be discriminating based on that factor for certain tests. So one of the things we did, we had a click track. We observed the subject's muscle movements according to that click track. That gets faster and faster, it accelerates. And at the same time, we measure the electromyography from those movements, okay? And we do this so that we can determine how well the muscles function for each of our subjects in the cohorts. So this is really cool. This is actually my favorite part, but when we record those electromyographical signals from the subjects who perform those movements in time with the metronome, who perform them until failure, we can actually take the signals, make them control a virtual prosthetic joint through a dynamic model, and then extract their maximum movement frequency, okay? So this entire time in our field, and I think it's pretty pervasive, this attitude I'm going to describe to you, but this entire time, people think that amputation cannot be better than intact physiology. Like, right? You're missing components, you're missing actuators and sensors. How can amputation ever be better than a real leg or a real arm? This is how. we find that by using the muscle signals that we record from the test and making them control a virtual joint, we find that people who have the AMI can actually swing their virtual joint faster than their unaffected one. Okay, so this is the first time that we've actually demonstrated a super physiological performance capability from amputation. A lot of asterisks, right? Like, can it do anything beyond swinging really quickly? That can be tested in further studies, but basically, if there's, in the future, if there's like a stanky leg dance competition, you know who's winning, okay? And most importantly, if we look at the control subjects, the ones who do not have the agonist-antagonist relationship, their performance is just about the same or even a little bit worse, not significantly so, than their unaffected side, okay? So really cool, in my opinion. There's another test we can do. We can perform a free space control test. So here the subject is disconnected so that they don't get afferent feedback from the vibrations of the movement. They have visual feedback in this condition, and they're moving the toe to 3 distinct levels, okay? This is really hard when you don't have all your muscles and all the information back from your peripherals, okay? But they made it work, okay? So everyone did this test. We find that with visual feedback, the OMP subjects demonstrate the least amount of variance in terms of their steady state position. So when they move the toe and extend the knee in low, medium, high levels, they're the most accurate and steady. Makes sense according to the electrode test that we did earlier, and also the soft tissue advantages that the AMI subjects have. When we put a blindfold on and ask them to just feel it out, right? Move the knee to low, medium, and high positions in terms of extension. We find that actually, if you look on the right, these bars that you see, the vertical bars in between the 3 groups, those represent something called the Jensen-Shannon difference. It's a metric of how much information is between distributions. We find that the OMP subjects in the orange bars have the most information between the 2 movements. We can discriminate the best with OMP subjects what they want to do. And if you look for contrast at the control subjects in the black bars, low and medium look about the same. There's actually very little information to discriminate between low and medium. So there's a low and a high mode, but there's no nuance. So it seems like things are working. One thing we can also do is this obstacle drill test, where you have to go over and back the blocks as fast as you can within a 30-second window. This is a control subject. You can see when they impact on the other side of the blocks, there's an unintentional flexion. Touching the blocks is failure, by the way. So the subject failed those tests. And the reason for that, we think, is due to impact artifacts, like I mentioned earlier, which were unable to be filtered out by our algorithm. So that subject is all the way on the right side. The top is the knee angle, so the trajectory. The bottom is activation for the corresponding trajectory. So we have represented here that exercise you just saw. If you look at this red bar, they're impact artifacts. That's that huge spike that looks nothing like what a muscle does. And for contrast, if you look back all the way on the left set of figures, that's an OMP subject. Really, really smooth trajectory on top, and really smooth and consistent activations on the bottom. And in the middle, we have an AMI subject. Even AMI subjects have some issues occasionally. That's because they still use a socket. They suffer impact artifacts even if their soft tissues are improved. So in addition to impact artifacts, we also see like electrode separation from the socket occasionally too. Like that's the nature of having these surface electrodes which you take on and take off each time. And here, like I mentioned before, every subject performed several types of drills. So these 4 types of drills that you see on the top, they performed as many as they could in 30 seconds. And then we counted them and saw how many successful ones they did out of the ones they attempted. So basically, everything along that diagonal is a perfect score. And if you have a score, if you have fewer successful attempts than the ones you tried, then there's a penalty, right? So OMP, almost perfectly accurate. Control subjects, pretty inaccurate. AMI somewhere in the middle. We did another test where we blocks as quickly as the subject is doing. So things are working. Our controller, our stack works. Okay. So we can look at the performance score here. So higher scores mean that they did better. And we have a rubric for this, of course. But essentially, after looking at the mixed effects model that we generated, we see that OMP subjects, when combined with AME subjects at the K3 level, they perform significantly better than control subjects. We don't see this advantage for K4 subjects, of which there are AME control subjects. I think that's because of the additional physicality component of the exercise. You can compensate to get over blocks with the rest of your body without using the neural control feature. Okay, and then what does this all mean? So what's the point of all this, right, in the end? Not only do we want to improve performance, we actually want to make people feel good too. Let's talk about our feelings now. When you use your limb, you feel integrated with it. You feel like it belongs to you, so there's ownership, right? You feel like you're in control of it, so there's agency. And you feel like it looks like your limb. It looks like a human appendage that belongs to you, so there's body representation. This is all to say that prostheses should really mimic biology. A prosthesis that is more physiologically correct is a better prosthesis. It's not just about performance and control. It's about how it makes you feel. So we gave a survey. We administered the same survey to all of our subjects in the previous experiments. We administered the same survey after each type of test we did, and we compiled all those results here. We find that only the OMP subjects demonstrated a significant improvement in embodiment for especially agency and also ownership partially. They're the only ones who actually benefited in terms of how they felt about using the device, okay? What is it because of? Well, probably some influence of all the things that we added to make them feel like that. But there's more to be studied in the future. But anyway, so we not only accomplished our task-based goals, but we accomplished our psychological goals too. What does that really mean? I mean, what does that mean in terms of like a subjective?
This is good. Oh, I love it. It feels like it's me. It's me, Tony.
He's just walking, but it matters, right? All these little things that we've added, they matter. So to summarize, I characterized the OMP's outsized ability to offer improved performance despite physical challenges. And then I also demonstrated super physiological capabilities from amputated physiology for the first time in this aim. Here's a publication that we're putting together. I think it's a big one, but we'll see. I have to be humble for now. Conclusions. There is a biomech knee controller that exists. I found it. Is it perfect? No. I mean, there are a lot of engineering challenges to really get this technology out there. But we found something that works, and that's in science. If you can find a binary yes/no, that's really great. You have something to talk about. We find that improving neuromechanics and improving hard tissues can actually improve control of powered knee prostheses. So does our approach, our heuristic of let's change biology and mechatronics, does that work? I think so. Finally, I didn't talk about this very much because it's not something that we tested, but we may need to actually provide more feedback to the user so that they can feel more in charge and more incorporated with their prostheses. So we might need to stimulate the muscles to provide feedback about the environment. We might need to provide cutaneous feedback so that they can feel what they're touching, things like that. We're working on this. Oh, I'm done. That was it. Okay, so I have a few acknowledgments, but should we do those first before the question? Okay, all right. First and foremost, I'd like to thank Professor Hugh, Herr, my advisor for these past, 5 years for the PhD. We'll go with that. When I first came to MIT, I was wrong almost all the time in our discussions. And since then, we've had more interesting discussions where I'm not always wrong. And I really respect your vision that's allowed me to gain that understanding I have learned a lot about academia, a lot about science in my time here, and I couldn't have gotten that perspective in any other way, in my opinion. I'd like to thank Professor Rickard Brånemark, MD, PhD, taking his father's work in dental implants and actually finding a completely different but very, very useful application for it. I mean, that's a huge amount of work to get osseointegration working at all levels of amputation. And so I respect your efforts. And this project would not have been possible without you. Finally, I'd like to thank Nidhi Seethapathi, my third committee member. Hogan, Neville Hogan, he's getting more mature. And impedance control came out 40 years ago. We need impedance control V2 to make the next step function improvement in rehabilitation, in my opinion. I think he might be the person. You respect the level and type of work, and I respect that. So thank you for doing research in your area of expertise. I really look forward to seeing more of those results, and I appreciate your thoughts and insights over my entire time here. Thank you. I'd like to thank Professor Max Ortiz-Calan, who's not here, but he also did a lot of work on EOPRA with osseointegration with electrodes and all of that on upper extremities, and he laid the groundwork in that domain. I reference a lot of his papers. I'd like to thank our brave test pilots, everyone who comes in and dedicates their bodies and their time. I mean, the most annoying thing about me is I'm like, oh yeah, we'll do it one more time. Yeah, just one more time. And that's never the case. I always lie. But they keep coming back for some reason. I think it's because of the $20 an hour that we pay them. That must be worth it, right? One more time. Just one more. Lindsay Reynolds is our senior executive administrative assistant. And Hugh is Polaris. Lindsay is our navigator on the ship. We would not be moving in the water without her. So I dedicate this slide to you. You've been an amazing help in my 7 years here, and I can't thank you enough for all of your efforts. We'll go quicker now, I'm sorry. I know it's like a lot of people I want to thank, but it's my defense, so. So Biomech, and in particular, the transfer warfare specialists, these people, I mean, mechatronics and hardware is really difficult. I think mechatronics is harder than the science. The science is like, okay, yeah, you just think of some hypotheses and test them, but to debug mechatronics and make hardware that works, I mean, oh my goodness, like years and years of effort, blood, sweat, and tears. I did it with these people, so we are brothers in a sense. I thank each and every one of you. I'd also like to thank the good, tolerant people who I have great discussions with, who I annoy consistently. Thank you for actually teaching me very detailed and specific things that I would have not have understood otherwise. And thank you for allowing me to come to this level of understanding that I have now. Back support, okay, so I injured my back. I pulled my back at one point, and then Samantha and Aisha actually brought me back to my apartment. They made sure I got back safely, so I really appreciate that. It's important to me that I can walk. And Zan, also our lab administrator and our assistant, really just making sure the ship runs too. So thank you. I'd like to thank all my Europs, in particular these, people from several years ago, people from now who are operating the camera in the back. Yeah, I can't do all this work by myself. I need help. And I just hope that you've also received some intuition, some benefit in return. So thank you for your efforts. My old mentors, I haven't forgotten about you, but even when I was like a really annoying high schooler or undergrad and I was calling you old and stuff, yeah, sorry about that, but I do appreciate you and all of the lessons that you've taught me. And even though we haven't talked in years, I'm very much proud to be your student. Our collaborators, especially Drs. Cardi, Rishov, O'Donnell, and Ferroni, people have to actually do these surgeries that I just kind of glossed over. There are details and there's patient follow-up. This is very hard work and it's extremely respectable. So without these medical specialists, we would not be here right now. So thank you for your contributions. I'd like to thank also Corey, Lori, and Rachel, who are basically our counterparts at Brigham and Women's, the hospital that we partner with. Kendall and Tyler Kleitz, who laid the groundwork in terms of establishing the grant for this OPR project, this OMP project. Yanmei and Laura, who helped with the fMRI analysis. Thank you so much. I also wouldn't be here without you. Our other affiliates over at the medical institutes, that keep the machine running. I'd like to thank Isaiah and Neil for this artwork, the amazing artwork that you saw. I did not do hardly any of that. I needed help, and so thank you for all your contributions and your hard work to actually helping me explain the science. And then Emily Rogers and Rachel, your slides, the thesis slides came in super helpful. And that's why I actually put together a cohesive presentation. And our sponsors, the K. Lucy Young Center for Bionics, DARPA, Integrum, NSF. I mean, money makes the world go round, it also makes research go. And finally, I'd like to thank my kids, my 40+ kids over the years at various times. NH3, my undergrads who I live with as an RA. You make me simultaneously feel 20 and 40. And I think that's a very interesting perspective, but I'm here for it. I really appreciate it. My friends who are far away, but who keep in touch and make sure I'm okay, especially when I don't respond for a long time. And then my family and parents, thank you for letting me just do my thing. I've always been a very to myself type of person, and they respect that. And you know, I'm here now, and it's because of your ability to help me and watch me grow. And I can't be thankful enough for all of you. So, all right, that's everyone. Thanks.
Nidhi, thank you so much. It was a remarkable presentation. Let's open it up for questions. Who's brave enough to go first? Rick.
Yeah. Can you think of any control or mechatronic improvements that need to be made that would make a difference, you know, as we take the next steps and things like this?
Right, so...
And then the second question is, what level of difficulty do you envision for doing a 2-DOF, adding a powered ankle? And, yeah.
So to answer your first question, the component that I really recommend John, my spiritual successor in the lab, implement is a axial load cell so that we can detect not just ground contact or no ground contact, but we can detect force development, velocity, and rates too. So are we loading fast? Are we unloading fast? That's really important for getting ahead of the impedance of the mechatronics. And you see commercial devices use an axial load cell. So that's what I would have done if I had a little bit more time. I really think that it takes our current mechatronics, our current hardware to the next level. It makes it way more responsive. And to your second question, which was?
Second DOF, a powered ankle prosthesis.
2-DOF is hard because I don't know if everyone understands this, but our bodies are incredibly weight efficient. We don't keep excess weight around in terms of our musculature, our bones, all of that. The thing is, like, metal is heavy, typically speaking. To add a second DOF, so like an ankle, you really have to minimize your distal inertia. And currently, I think the power density of electromechanical systems is almost there, but it's really hard. You don't have a lot of tolerance. So in my opinion, that is the challenge. Adding useful torque and power generation without being too heavy and wasting all of that metabolic gain that you get from the power.
Jump in. What do you think the impact would be? You say single knee. What do you think the impact would be of using multiple knee angles?
So the question is, if we added more AMI constructs for knee control, what do we actually get in terms of performance or measurable differences? One reason why we don't do direct control, as in calculate a force for each knee muscle and then just apply it, you know, maybe through some geometric transform to the joint is because we're missing a lot of information. Our joints, typically, they have a lot of redundancy in terms of their controlling musculature. It's not just an agonist and antagonist pair. It's actually multiple muscles acting as an antagonist or agonist sometimes, and then working against other muscles which are either activated or not activated sometimes. So the benefit of having redundancy in terms of a knee AMI, maybe we rely less on this intermediate impedance calculation. Maybe if we had every single muscle preserved, so that we actuate internally around a very low impedance joint, maybe then we don't actually need this impedance calculation which fills in the gaps. We can just do direct force torque control, and it works. So that's a thought there. If we don't get there, then at least we have more information with which to inform the impedance layer and get more accurate, safer control.
Yeah, I was wondering, did you ever investigate any type of adaptive control techniques in the sense of, I would assume probably one of the issues maybe like trying to tune your control loop depending on whether a moment of inertia of your leg or any other issues like that. And then two, did you ever do any type of thing where you would feed back electrical signals back into the nerves itself? Because I assume you read the electrical signals from the nerves, but do you send any signals back?
Yeah, so first question, did I investigate adaptive control for the knee joint? The most adaptation I do is I estimate walking speed on level ground via swing and stance time of the previous step. And this is only done to compensate for the impedance, the inertia of the knee, the mechanical inertia of the knee. So for walking faster, I have to apply more torque at the knee, more current to make it swing up and out of the way. The reason I didn't investigate adaptive control, and I think in the way that you're really talking about, is because I didn't think I needed it. I figured, or I prayed that I could get away with relying on the intelligence of the human. Sometimes that works and sometimes that doesn't. In my case, I lucked out with my subjects. But if we just let the amazing thousands of mechanoreceptors and biological amplifiers of the human do their job, relying on the central nervous system, which is the most amazing control that we know of, then we can get to somewhere like here. If I were to add an adaptive controller, that's just, that's sugar on top. I could probably make that better. Maybe John can investigate that. And to your second question, did I investigate feedback? I investigated feedback very briefly. I have a slide here which I can pull up. I determined the sensation map from functional electrical stimulation on the individual electrodes in both monopolar and bipolar configurations. And I did this just to determine the plausibility of applying feedback in a future test. Feedback is very difficult to apply, especially during gait-related tasks. Lots of things are moving. And also, it precludes EMG reading and simultaneous feedback. So here, I found the slide. So here's the sensation map that I determined for both of our OMP subjects. When I just applied current through the electrodes, a standard, very basic and uniform signal that you can see on the top left. And I determined just where they felt the sensation. I didn't sweep the parameter space to determine like what types of sensations they felt, but in my testing, I got everything from paraesthetic sensations like buzzing, vibrations, all the way to proprioceptive feedback in the appropriate places. So there's hope there. If we had better hardware, better stimulation hardware, better, more flexible EMG hardware so that it can work with the stimulation hardware, then we could maybe really test this hypothesis out. People in our lab are investigating for other subjects. So it's definitely the right direction to go. It's more natural. I didn't get there in time. Yeah.
Do you feel like the sort of measures of functional performance that we have available in the literature are good enough to sort of test performance in super real world contexts? So the kind that you're trying to go towards, like thinking about uneven terrain and sort of obstacle navigation and things like that. Do you feel like we have the right quantitative tools to even say they're doing better or not in those contexts?
Right, so the question is whether or not the things that scientists are looking at have reasonable application in the real world, as in, are the tests that we've developed to characterize gait and performance, do those directly relate to how well someone actually does once they're out of the lab? I think honestly, no. My opinion is that we've developed tests which are testable, if that makes sense. So there's a lot of stuff that happens out in the world. Once you let someone run loose out there, who knows what's going to happen? In the lab, we develop metrics and tests which we can control very carefully, which maybe have some relation to performance. But we make them achievable within our testing period. And we don't follow up long term because that's very expensive, and we don't look at all these other variations because that's very broad and difficult to put together in terms of an experiment design. So yeah, my answer is I don't think we're quite there yet, but we really should. And that's why I think currently in our field, our broad field overall, these papers that you read about take-home experiments, even if they test very basic functionality, that's why they're so impactful, because they actually let someone take an experimental device home and then they got some data about it. And it just, in a lot of ways, it tells us a lot more than what we can test in the lab specifically. Guillermo.
Yeah, amazing defense, Tony. I think you show like a pretty dramatic increase in ownership between like OMP and AMI. Do you attribute that mainly to like OC perception, or do you have like any other, like what's your explanation to that big increase?
So the question is, why do the OMP subjects perform better than the AMI subjects? At least in the lab, the lab conditions that I tested. So one thing in particular that we did get data for are the electrode characteristics, right? So with surface electrodes, we don't actually talk about this very often, but with surface electrodes, I'm replacing them every hour as the person sweats, as they start bridging because of that sweat. And all the conditions that I've tested were with, nominally properly working electrodes. That doesn't mean I caught every single slip, right, or every single loss of information. So at least from that perspective, part of the performance delta can be attributed to just interfacing technology, electrical muscle interfacing technology. Regarding osteoperception, yes, that exists. People, or the two subjects I tested with, definitely told me when they felt, jolts going through their bone, when they felt loading on it, when they're sensitive to this, that torque in a certain direction. Whether or not that informed their behaviors and capabilities, I can't say because it's hard to measure osteoperception, but I would not be surprised. So that's the next step in my opinion. If someone can measure how much osteoperceptive information the subject gets as afferent feedback, huge result. A, it develops new tools, and B, it tells us something pretty deep about physiology.
Chris? Yeah, I can just say my question out loud. Yeah, great job, Tony. It's been awesome working with you. My question is centered around training and use time of the prosthesis. Did you observe or plan to study any effects of training time on both the functional metrics and the embodiment measures?
Yeah, so the question is whether repeated exposure to the device or use of the device in specific ways helps raise the sense of integration with the device itself. It does matter a lot, right? A lot of these experiments in our field, and even these, I think kind of gloss over that aspect, but training is hugely important for how well you integrate. But the valence might be actually in the opposite direction from what you expect. And what I mean by that is, in my AIM-1 experiment, I didn't actually talk about this, but exposure to the device, once you get over the novelty of, oh, I can flex my knee, I can extend my knee. Once you get over the novelty of just having binary movement in a single direction, it kind of, you start noticing the things that it doesn't do well. So flexing, extending at 100%, great, makes you feel good for the first 2 days. And then by day 5, day 6, it's like, well, I wanted it to I wanted to lift my toe 1 inch off the ground, but it went 2 inches off the ground, and I don't like that. So we actually do have data for that in our embodiment questionnaire for AIM-1. I just don't report that data here for brevity. But I think they find this phenomenon in upper extremity cases where they look at embodiment. I have a slide actually. I've coined a term for it. You know how there's the hedonic, look at point 1, look at the hedonic treadmill. I call it the embodiment treadmill. Give a mouse a cookie, right? Give a person with amputation a neurorobotic prosthesis. Then they want all these other features. Then they want feedback. They want really fine-grained control. They want to take it home. They want to buy it on the market. But it's something that we can definitely investigate. I think few people are talking about it, just exposure and what that does to your perceived level of embodiment, whether it raises your expectations or not, all of that. Okay.
Great. Should we check online? The folks online, do you have any questions? Rickard, Brånemark, or?
Oh, hi Tony, it's Roshan. Can you hear me?
Yeah, I can hear you.
I have a question.
Yeah.
I was actually curious about like what challenges you faced when you melded taking the input from the human body and then also the sensors from the actual prosthetic. You're talking about the function F that puts those together.
Right, right. So the hard part about developing those two aspects together is that you don't know where the problem is coming from. In the very beginning, I was thinking that I could get away with just the neural control layer. What if I just modulate impedance with our muscle activation information, right? Because the human is so amazing. So I was humbled. I spent a lot of time on that, and I was humbled. But what I realized is that the problems I was facing were really based on the mechatronics and the system dynamics of such systems. So the additional reflected inertia from the transmission ratio. Once I compensated for those nonlinearities, I was actually able to get much more performance out of my neural control layer. So that is the difficult part. But my claim that I provide no evidence for, my claim is that if you just take the neural portion of my controller and you apply it to a clutched knee, something that can swing freely without the additional reflected inertia, you can just overlay those two aspects in parallel. You can have the neural layer running in parallel to whatever passive dynamics of that clutched prosthesis are doing, and it should work. My compensation layer, my mechatronics finite state machine, that's really, really just to get the knee swinging because of the heavy motor and transmission. So I think hopefully that answers your question.
Yeah, that was not what I was expecting. Thanks.
Okay. That's science sometimes. You don't see what you're expecting.
Anyone else online?
Yeah, this is Rickard. Greetings from Gothenburg, where actually our situation started 2 years ago. Tony, great work. Maybe you should add more emphasis on biomechanics and also perception, and so that is sort of coming freely. But I was more thinking about now you have some kind of invasive methods and you pick up myoelectric signals, but you can also maybe instrument others. I know there are other attempts to do, but just to give you an idea what I'm thinking. So say that you put also strain gauges on top of the muscles of the agonist, antagonist. Could that, or what kind of additional information would you like to have from the biological constructs to make the movements smoother and pick up intent earlier?
Oh, okay. So the question is, what other information can we gain from muscles or soft tissues in general to actually get improved performance? EMG is a very, in my opinion, crude way to estimate muscle state. So it does the job, but we have to do a lot of filtering, and once you do all that filtering, you have a group delay of something on the order of 150 or 200 milliseconds. So everything is delayed. EMG is susceptible to noise, and the signal-to-noise ratio is actually, it's usable, but it's not ideal, in my opinion. So the alternatives are, how else can we measure muscle? Our lab is looking into that quite deeply. So in other areas of research, they're looking at implanting magnets into the muscle. And so if you can track magnet state, magnets which are affixed to known relative locations within the muscle bellies, for instance, then you know muscle state immediately. You actually don't need to pass them through this electrode filtering that we do. And so perhaps you get information at a faster update rate than 150 milliseconds or 200 milliseconds. So with EMG, we actually have to filter that. Then we get an estimate of the muscle state. What if you can just measure muscle state directly? Yeah, that's kind of the way to go. Let's use magnets. Or I haven't heard of the strain gauge technique, but theoretically, same benefit. It could work.
Great. Rick, did you?
Yeah, thanks. Sort of just paving the way for some of the future research ongoing after that.
Right.
So 36 million people fall a year in the United States. What indication do you have that the work that you did improved balance? Were you able to take any measurements that in the different cohorts that you had that were within each patient, that there was an improvement, that embodiment was partly related to an improvement or was accompanied by better metrics of balance, that kind of thing?
So the main question is, did I look at balance in terms of my interventions and their outcomes? The answer to that is yes, there is actually a small section that I have in balance. So for the OMP subjects, I looked at their level ground walking on the treadmill with their passive devices, so their prescribed devices, after the intervention. Okay, so we have that here. It's a little bit messy, but in the bottom subfigure, you can see that there's a symmetry index, 1 being perfectly symmetric, less than 1 indicating that you favor your sound or unaffected side. Okay, so I have pre-op data, I have post-op data, I have post-op neural with our finite state machine based on the knee. So those are the 3 colors. What we find is that for subject 1, or OMP1 on the left side of the bottom subfigure, that subject actually experienced better symmetry. Symmetry index closer to 0 is better. So that subject actually got more symmetric after the intervention, after recovery and all of that, with just their prescribed device. However, if you look at the right side of the subfigure, the gray is higher than the black, as in the post-op prescribed condition is less symmetric than the pre-op prescribed condition. That subject actually got less balanced. There are a lot of complications, but what I hypothesized to be the case is that OMP2, during this entire time of testing, that subject reported sensitivity at the abutment. And in my previous slide on the timeline of OMP integration, we find that this sensitivity can last 1.5 years to 2 years, even after the second stage. And it takes some people longer to integrate with the implant completely. But if you are feeling, if you're feeling every step, if it's like a level 2 out of 10 on the pain scale, then it's going to throw you off. So in my tests, I didn't explicitly test balance in all conditions that I administered because that wasn't necessarily the variable of interest. But there are a lot of things that affect balance which aren't necessarily related to control itself. I think it really has to do with individual factors and perhaps timelines to recovery that we didn't account for strongly in this experiment.
Thank you.
Great. One last and very important question. Could you explain your clothing?
Oh, yeah. So this is, I don't even know if it's traditional, but it's a Chinese robe from based on Ming Dynasty clothing. My father sent it to me from China because I wanted one, and then I figured, well, if I have one, then when can I even possibly wear it? So here we are at the most important event of my academic career, perhaps. And yeah, and he's in a onesie, which we agreed upon beforehand.
Thank you, Tony.